Hello guys. So let's quickly talk about heat engine. So heat engine is a device that converts heat energy into mechanical work. That is heat engine. It converts heat energy. It converts heat energy into mechanical work. And how does it do that? It does that by operating between two reservoirs. These are the two reservoirs by operating, though the operation is in a circle. Not circle like this. That's not what I mean by circle. Okay, let's say this the first reservoir, this is the second reservoir. By operating between these two reservoirs, heat engine convert heat energy into mechanical energy. And the two reservoirs, one of them is the hot reservoir and the other is the cold reservoir, like I draw in this diagram. So this is our quantity of heat. This Q hot reservoir, this Q cold, QC cold reservoir. This is the temperature of the cold reservoir. This is the temperature of the hot reservoir. This sketch is a sketch for what? Heat engine. And what does it do? Heat engine convert heat energy into mechanical work by operating between two reservoirs in a circle. The two reservoirs were the hot and the cold reservoir. And please take note, how does it do the operation? How does it know? We said it converts heat energy to mechanical work by operating between in a circle, right? But how does it operate? It operates by extracting heat or heat energy from the hot reservoir. And when it extracts heat from the hot reservoir, the next thing it does is to convert the heat that is extracted here into work. The heat extracted from this hot reservoir, heat engine converts it to work. But note, it is not everything that can be converted to work according to second law of thermodynamics. That's Planck's law, Planck statement or Kelvin Planck statement. He said all the heat extracted from the hot reservoir by an heat engine cannot be converted to work. Everything cannot be converted to work. So when we extract heat from the hot reservoir and we are converting into work, the heat engine is converting into work. Some of those heat that is extracted from the QH is rejected to the cold reservoir. So which means the one that is converted to work is equal to the one that we extract minus the one that is rejected. So do you need to cram this? You don't need to, because it has been explained already. And whenever you remove heat from here, as per se you be heat engine, you remove heat from here, you are converting into this one. Some is going here, some will be rejected here. So the one that you convert to, which is work, if you want to find it, it is the one that you extract minus the one that is rejected, isn't it? So this is it. Now, the efficiency of a heat engine coming. The efficiency of an heat engine, EFF, equals to the work that we convert the one we extracted from the hot reservoir divided by what? The one that we extracted from the hot reservoir. Work done over what? Work over QH. And note, our work is QH minus QC, isn't it? So this can be written as what? QH minus QC over what? QH, isn't it? So we can conclude that efficiency can also be what? QH over what? QH minus what? QC over what? QH. And that's what? This one, right? Minus what? QC over what? QH. Isn't it? So you can have different formula for it. Work over QH minus QC over QH, because this is same as work. Then QH over QH, which is equal to 1 minus this. I hope that's clear. So, but take note, efficiency of an heat engine can never be equal to 1, which means it can never be 100%. If it is 1, that's 100%. If it's 0.25, that's 25%. If it's 0.5, that's 50%. So it can't be 1. That means it can't be 100%. Only perfect engine can be that, and perfect engine does not exist. An engine with efficiency of 100%, it doesn't exist. The highest efficiency we can have is the one of Carnot engine. Are we together? And Carnot engine, you can't even buy it like normal car engines. It's not something you can buy now as if we have it all around. Oh, I want to buy Carnot engine. No, it's an engine created by, what's its name? Let's not even go there. Are we together? But we can't buy Carnot engine in the market, which means even Carnot engine now we can't make use of it. But it's just like like I don't want to call it a limit now because no real engine can even get to the point of Carnot engine. But let me just say it's just like the highest we can ever achieve as far as efficiency of an heat machine is concerned. For instance, let's say since the efficiency of a real engine can never be equals to 1, what does that imply using this formula? Efficiency equals to 1 minus QC over what? QH. If efficiency cannot be equals to 1, it means QC can never be equals to 0. Because the only reason why this guy will be equals to 1 is when this equals to 0. It's not even this, because if QH is 0, you can't divide by 0. Do we get? You cannot divide by 0. So QH is not even 0 before. But QC also can never be 0. QC can only be 0 for a perfect engine. And that is against the law. See, all these things are very simple. That is against the law of a statement of Kevin Planck. If QC is 0, that means all the heat we extract from QH is converted to work. Nothing is rejected to the QC. And Kevin Planck, second law of thermodynamics, says no, impossible. Heat extracted from the hot reservoir can never be converted, or everything can never be converted to work. Some, no matter how little, must be what? Rejected to the QC. So QC can never be 0. In that case, efficiency cannot be equal to 1, which means efficiency cannot be equal to 100%. I hope I'm getting clear at you. So that's that for that. So, yeah, this is the formula. So we also have efficiency of a real engine is always less than 1, because this one will be greater than 0. The only time that this can be equal to 0 is if QC is 0, and since QC cannot be 0, this will always be greater than 0. Are we together? So if you remove something greater than 0 from 1, that thing will, your final answer will always be less than 1. So efficiency of a real engine efficiency is always less than 1. Is that clear? So use the formula for real engine. Now let's move on to Carnot. Now you are going to see what I'm talking about now. Carnot engine. Now for Carnot engine, how can I put it now? Oh, I'm looking for a way to put it. Okay, before I explain, let me give us the formula first. Carnot engine, the efficiency of a Carnot engine equals to 1 minus. Now you know for a real engine we use what's it called? QC minus QH, 1 minus QC minus QH. But for Carnot engine is TC over TH. Do we get? We use this formula to find the maximum efficiency possible. Take note, for Carnot engine, also QC over QH equals to TC over TH for Carnot engine only, which means the formula we use for real engine, EFF equals to 1 minus QC over QH, can also be used for Carnot engine. Now, this is the difference, and this is the problem. You can never use this for real engine, this formula. You cannot use it for real engine, but you can use this one for real engine, whereas you can use both for Carnot engine, because in Carnot engine, this is equal to each other. Why? Because Carnot engine is it gives you the maximum efficiency possible. That's why we can also use this for Carnot engine. And this, let me repeat again, you cannot use this for real engine. It's only meant for Carnot. This is the one you can use for real, but you can use both for Carnot engine. Now, Carnot engine is an ideal engine, but it's not a perfect engine. Now, many of us, we misunderstand the meaning of an ideal, because most time we think ideal is always 100% efficiency. No. Are we together? But we don't have time for that today. Take note, for this particular topic, ideal is not about efficiency being 100%. Take note of that. Ideal, the idea of ideal here under heat engine is just like when we are saying, this is the highest point you can ever get to. You cannot exceed it. It's ideal, like you can, and that highest point itself, no real engine can get to it. So since no real can get to it, then that means that point is no longer real. That's why it's not an ideal. Even that ideal point is not even perfect. Perfect is the sense that it's 100%. No. Now, for note, a perfect NG with efficiency of 100% does not exist. Carnot NG exists, but the fact that it exists is not something you can buy in the market. Real engine are what we are buying today. Car engines, grinding machine engines, those are real engines. They are not Carnots. You cannot even buy Carnot, but it exists. But perfect does not exist. The efficiency of real engine is less than the efficiency of Carnot engine, and that Carnot engine is less than 1, or you say it's less than 100%. So this is the for perfect engine, QC equals to 0, but this is not possible. So perfect engine does not exist. And one thing you need to take note, please, this temperature, they must always be in Kelvin. If not, you are wrong. They must always be in Kelvin. And the fact that our TC can never be 0. Why? Because under law of thermodynamics, no, it's not possible for you to obtain a 0 Kelvin. No. This is arbitrary. It's not possible. So TC can never be 0. Even so, that's why even Carnot engine cannot have efficiency of 1. Carnot engine too cannot have efficiency of 1. So for TC to be 0, we are already going against thermodynamics. And that is only for perfect engine. And that's why perfect engine does not what? Exist. I hope that's clear. Please take note. Convert this temperature to Kelvin before you do your calculation. Now let's check few calculations before we proceed. So this is a question now. The input energy of an engine or of a heat engine is 3 times greater than the work it does or the work it performs. What is its efficiency? Now we are told that the input engine, note the input engine is always the QH, the input energy rather, QH. Well, is where we extract. That's where we collect. So it's the one that is coming, the input energy. 3 times greater than the work it performs. Is that clear? So QH equals to 3W. What is its efficiency? We know that efficiency equals to what? W over what? QH. It depends on what you are given. You can use 1 minus. We've proved that earlier. It depends on the value you have. So here now, it means, how can I put it? QH is 3 of W. That means W will give us what? I'm looking for a way to factor that. Now QH is 3 times this. So this means this 1 over 3. I hope we get that. QH is 3 times this. 3 times this. That means if this guy is 9, this will be 3. Since QH must be 3 times, do we get? So there's no problem about that. QH is 3 times greater than the work, 3W. So efficiency gives us W over QH. That's 1 over 3. If it is 4 times, 1 over 4. If it is 2 times, 1 over 2. I hope that's clear. So that's efficiency. Now, what fraction of the input energy is expelled to the cold reservoir? Efficiency, we say our efficiency is 1 over 3. And what's 1 over 3? Is 0.333, right? Or we say 33.33%. Equals to. Now, don't forget. The efficiency is same thing as efficiency is this equals 1 over 3, and this is the 1 over 3 here. The same thing as 1 minus QC over QH. Do we remember? The efficiency is also equals to this. So now, what we are looking for what fraction of the input energy is expelled to the cold reservoir. Now, here now we have, so let's take this to the other side. QC over QH equals to 1 minus what? 0.333. Are we together? If you take this to the other side, you have 1 minus 0.333. So at the end of the day, QC over QH equals, if you subtract this, what do you get? Is 0.667. So is that clear? So this is the fraction. The fraction of the input, this is the input energy, the fraction of the input energy that is expelled to the cold reservoir. So this is let me check. Yeah, that's what we asked to find, but I'm checking something. If work is 1. Oh, okay. I think what we are looking for is QC. What fraction of the input energy is expelled to the cold reservoir? So we are looking for the amount of energy that goes to the cold, that went into the cold reservoir. So cross multiply. QC equals to what? 0.667 of what? QH. So these are QC. So this is the fraction of the QH, yeah, that went to QC. This 0.667, we can rewrite it as QC equals to what? 2 over 3 QH. 2 over 3 is 0.67. So 2 over 3 is the fraction of QH that went to QC. I hope that's clear now. Sorry about, I was checking. So this is not what we want to find. QC is what we want to find. That is, what do we have at QC? So I hope that's clear. So the next question. Pardon my writing, I'm sorry. So an engine transferred 2.0 times 10 raised power 3 joule of heat from a hot reservoir. QH equals to 2 times 10 raised power 3 joule. Are we together? 2.0 times 10 is the same as 2 times 10. And also transfer this to the cold reservoir. So our QC equals to 1 times 10 raised power 3 joule. This. So find its efficiency. So our efficiency, don't forget. Now I cannot use this. I cannot use W over QH because I don't have W. So, but I know the efficiency is 1 minus what? QC over what? Q what? QH. And that gives us 1 minus what? What's our QC? This 1 times 10 raised power 3. What's our QH? 2 times 10 raised power 3. Isn't it? This cancel. So we have efficiency equals to 1 minus 1 over 2, 0.5. And our efficiency is what? 0.5. And that's same thing as what? 50%. 50%. I hope that's clear. It's no go far. So the next one there is how much work done by the engine, or how much work is done rather by the engine in a circle. They can ask you in 2 circle, in 3 circle, but this is in 1 circle, in a circle. So now we know that our efficiency, what do we get earlier? 0.5 equals to W over what? QH. I hope we do not forget. This another formula. Efficiency is W over QH. We use 1 minus Q over QH earlier because of the value we have. Both are actually equal. So if we cross multiply, that means W equals to 0.5 times what? QH. Right? Oh, sorry. The light. I hope we can still see it, sha. 0.5 times QH, and that's what? 0.5 times 2 times 10 raised power 3, and that gives us what? 1 times 10 raised power 3 joules. So this particular question means that the work done is equal to the amount of energy that is transferred to the cold reservoir. And we can even see that that is correct. So the formula valid, because if you add this work done to the QC, it gives you QH. And something like that, we've discussed it earlier. So that's that for that. So the last question now. So let's end it with this. The video is getting long. The hot reservoir of a heat engine at 100 degrees C. So our TH equals to 100 degrees C, convert to Kelvin. If you add 100 to 273, equals to what? 373 Kelvin. If you don't use Kelvin, you are doing another thing, and you will see the answer in the option. So our TC, transfer heat QH, we are given QH equals to what? 750 joules. Right? The hot reservoir of a heat engine at TH of this, transfer heat QH this, and its cold reservoir at 0 degrees C. So 0 plus 273 equals to what? 273 Kelvin. Receive. This one transfer, this one receive. QC equals to 120 what? Joules. So we ask you, what is the maximum efficiency? Now, when they are talking of maximum efficiency, let your mind go to what? Carnot energy formula. Whenever you hear maximum efficiency, let your mind go to what? Carnot energy formula. And what's the efficiency for Carnot? 1 minus TC over what? TH. No, you can also use QC over QH. But because this is a real engine, though it's not same thing as Carnot, I don't know how to put it now. No, for Carnot, actually, you can use QC over QH. But because it's not Carnot, what I'm trying to say is that whenever you hear the word maximum, just remember to just use the idea of Carnot. That's what I want to say. Even for Carnot, it's TC over TH, even though you can also use QC over QH for Carnot, because in Carnot NG, QC over QH equals to TC over TH. But in real NG, they are not equal. But whenever they can't, but whenever they are talking of maximum, that first formula for Carnot, let your mind go there. So our efficiency now equals to 1 minus or TC. What's our TC? TC, which is 273 divided by what's our TH? Our TH is what? 373. So whatever you get, that's your final answer. I hope that's clear. So that's the maximum efficiency possible. So thanks for watching. Don't forget to like and subscribe. Thank you. And share.